This educational material is prepared by Dr. Nima Madian. Welcome to this explainer, everyone. Today, we're embarking on a genuinely fascinating engineering journey. We're going to completely dissect the anatomy of a PLC motor control start/stop circuit. Basically, we'll trace the entire sequence of events, right from that first momentary physical push of a button, all the way down the line to sustained continuous mechanical motion. Okay, let's dive right in. So here's our agenda for today's explainer. 1. Introduction to motor control. 2. NO and NC contacts. 3. Hardware wiring architecture. 4. Digital brain, ladder logic. And finally, 5. Anatomy of an action.
Section 1. Introduction to motor control.
Let's look at the core engineering challenge here, because it's actually a beautiful puzzle. You've got a physical push button. It's momentary by nature, right? You press it, you let go, and it physically resets itself. But we need that super brief physical interaction to result in a continuous, sustained mechanical output. So how do we bridge that gap? How exactly does a fleeting human touch become a persistent machine state? That right there is the foundational, academic, and really the practical puzzle of motor control.
And solving that puzzle absolutely matters, because this circuitry is literally the invisible backbone of modern automation. Just think about conveyor systems. They require continuous, relentless motion from a single momentary start command. Or consider heavy gantry cranes. They demand completely safe, fail-proof lifting operations that absolutely have to hold their state. And automatic doors. They need perfectly reliable mechanical responses triggered by highly transient sensor inputs.
So what you really should take away from this is that a momentary start-stop circuit is far, far more than just some textbook exercise. It's the fundamental building block of industrial control systems across the entire world. Whether you're, say, moving a tiny little package on a belt or lifting tons of solid steel in a shipping yard, the underlying logic block is exactly the same. It's pretty amazing.
Section 2. NO and NC contacts.
Now, before we get to the software, we have to understand the absolute physical prerequisites, the contacts themselves. Let's study the distinct physical and electrical states of these two buttons. First up, the green button. It's normally open, or NO. At rest, the circuit is physically broken, meaning no electricity can flow. Pushing it connects the circuit. Conversely, the red button is normally closed, or NC. At rest, the connection is already made and electricity flows freely. Pushing this button actually breaks the circuit. It's a totally simple physical difference, but it completely dictates the entire architecture of our system. Which brings us to an absolutely crucial design note regarding fail-safes. Why do we always use a normally closed contact for a stop button? Well, it's a built-in physical safety net. Think about it. If a physical wire is accidentally cut, maybe corroded, or just damaged by heavy machinery, the circuit physically breaks. Because our stop button relies on a continuously closed circuit to allow the machine to run, while that accidentally broken wire instantly and safely halts the machine. If we used a normally open button instead, a broken wire would mean we'd frantically press stop and absolutely nothing would happen. No way we'd want that.
Section 3. Hardware wiring architecture. Let's carefully trace the electrical wiring on this schematic together. Start up at the 24-volt DC power source. The power flows out, and it splits to our two physical buttons. The signal from our green, normally open start button routes directly into the PLC controller at the input terminal labeled IN1. Meanwhile, the power flowing through our red, normally closed stop button routes right into input terminal IN2. The PLC controller then acts as the brain. It processes these signals and then sends an output command labeled CR1 straight down to the DC electric motor. This is the complete closed physical loop required to actually make the whole shebang function. Now, I want to quickly highlight a small but vital engineering component we use in this setup, the diode. This provides what we call flyback protection. Here's why it matters. When a DC motor coil is suddenly turned off, the collapsing magnetic field can generate a sharp, massive voltage spike. That diode is strategically placed to safely loop and dissipate that energy. Basically, it protects the highly sensitive electronic circuits inside the PLC from getting fried by its own motor. Pretty clever, right? Section 4. Digital brain, ladder logic.
Okay, let's shift from physical wires to the digital realm. Here is the core software concept we use to solve our initial problem. It's called the latching metaphor. Remember our puzzle? The physical start button is momentary. When you let go, the IN1 signal disappears entirely. Well, the digital solution is right here in the software logic. We program a parallel contact underneath IN1, and we tie it directly to the output coil, CR1. So once the CR1 output is energized by that first push, it instantly and simultaneously closes its own parallel input contact. It acts as a digital memory seal. The power now has a bypass route. The motor effectively feeds itself the on signal, totally bypassing the released start button.
Section 5. Anatomy of an action.
Let's bring this all together and animate the thought process dynamically. In state 0, the idle state, the motor is totally off. Our IN1 contact is open, our IN2 contact is closed, just patiently waiting for a signal to pass through. Now look at phase 1, initiation. A physical finger presses the green start button. Instantly, the momentary push bridges the IN1 gap. You can clearly see the logical path glowing green. The path is complete, it flows straight through the closed IN2 gate, it energizes the CR1 output coil, and boom, the motor begins to spin.
Let's methodically lock in what just happened, step by step, just to be sure it's completely clear. Step 1 was state 0, our idle wait state with the motor off. Step 2 was phase 1, the initiation. The physical momentary push successfully bridged the IN1 gap in our digital ladder logic. That completed the circuit and energized the CR1 output. The logic of this initial strike becomes perfectly transparent when you map the physical action directly to that digital logic gate.
But what happens when the operator lets go? Well, in phase 2, the finger has stepped away. IN1 is visibly open again, but follow that glowing green path. Because the CR1 coil was energized, it is now holding its own parallel contact closed. The circuit successfully sustains itself. Then, eventually production has to halt. That brings us to phase 3, the stop. A finger presses the red NC stop switch. This physical action instantly opens the IN2 gate in the software. The logical bridge collapses completely, immediately de-energizing CR1 and halting the motor.
Just to really solidify our understanding here, phase 2, the latch, is entirely dependent on that energized CR1 coil holding the parallel contact closed. That is the critical bypass loop that continuously sustains power without human intervention. And then in phase 3, the stop, pressing the physical failsafe instantly opens that digital gate, severing the software path and safely de-energizing the whole system. Honestly, it is a flawless synchronization of physical mechanics and digital instructions.
Which leaves us with a final, really fascinating question to ponder as we wrap up today's explainer. How does this simple start-stop foundation scale up to orchestrate a massive, complex, multi-stage robotic assembly line? The truth is, every huge industrial system you see out there, no matter how intimidating or intricate it looks, is built on hundreds, sometimes thousands, of these exact, perfectly timed, self-latching logical blocks, all working in concert. Thank you so much for joining me today. I really hope this rigorous breakdown empowers you to see the invisible logic running the automated world around us